This video is going to be about basic friction. So first, let's talk about two concepts right here, which first we know what force is equal to. Force is equal to mass times acceleration, right? F is equal to ma. Now, the force of gravity is very easy. That is just mass times the acceleration of gravity, which can be written as g. And the acceleration of gravity, remember, g is equal to negative 9.8 meters a second squared. So that is F of g. That is force of gravity. So if something is falling, the force of gravity is this. The mass of this object times negative 9.8. Now, F of n is normal force. This is normal force. This is not net force. If you see net force, most likely they would actually write net force. So normal force and force of gravity. Now, in this scenario, if this is not on an incline, right, then this F of n is equal to the force of gravity. So F of n is equal to F of g, so the force of gravity, times cosine of theta. Now, this is on a horizontal plane right here, so the angle that's being created is 0 degrees. So if we were to do F of g times cosine of 0, well, cosine of 0 is literally just 1. So it would just be F of n is equal to F of g, and that's what happens in this scenario. These guys are just equal to each other. So they basically cancel out in net force. But, or if this was to be on the ground, it would cancel out on net force. Sorry. If it was falling, it wouldn't. There would be negligible normal force, and only the force of gravity would be in force. But if it was to be, so this would be like an example if it was sliding on the ground. This is if it's sliding on the ground at an incline, okay? So it's going like this way, or it could be going up. But for this example, it's going down. The force of gravity is always just going towards Earth. But then the normal force is always coming out of the ground. So basically, the force of gravity is gravity pulling the object to the core of the earth, right? So it always just goes straight down. But normal force is essentially the force that the earth is pushing onto the object, if that makes sense. So what that actually does is the earth, in this case, because it's on an incline, is pushing perpendicularly towards the object. So for the normal force is going this way. So that's why it's different in this kind of scenario, but they're completely perpendicular, or parallel, I should say, in this scenario where there's no incline. So now you know what normal force and force of gravity is. So what we're going to talk about is friction now. So frictional force is equal to normal force, right? Which is force of gravity times cosine theta. So normal force times, and this is called mu. So this is not pi. This is called mu. Mu. And basically what this mu represents is our coefficients of friction. So, I mean, you can just think about any example. Even think about this pen right here. This plastic is going to have a lower coefficient of friction. It's easier, it's slick, so it's easier for me to rub my finger along it. Now, the grip, right, has a higher coefficient of friction because it's harder to slip my finger across of it. And the reason why is that's why it's for grip purposes, right? So your fingers aren't slipping around while you're writing. It's easier to grip, and that's how you can think of coefficient of friction. The lower it is, which the lowest it can go is 0. 0 would just mean that there's no friction. So it's like moving your hand in air. And then very high friction, right, would be like this grip, or like on a skateboard, this grip tape so your feet don't slide around. And that would be a high coefficient of friction. So that's what the coefficient of friction represents. And it's represented by the variable mu. So frictional force can only be present if there is movement, right? Because if I'm not moving my finger on this pen, then there's no friction happening, right? So, for example, a box, standing here, there's no friction. Even though there is a coefficient of friction of this material, like the table that it's on, it's not moving, so there's no friction moving against the box. But the second this box starts moving this way, so like the applied force is going that way, then frictional force will always go in the opposite direction. And that just makes sense because when you rub your like finger or anything against anything, basically, there's always going to be resistance, and that is friction. So friction is moving in the opposite direction of where my finger's going. That's how it resists. It opposes the direction. So now we actually understand what mu, frictional force, is. So let's solve this question right here. So a person pushes on a 7-kilogram stationary box. So it's stationary and it's on the ground. So the ground's basically signals that it's flat. We're on flat ground. And this is a 7-kilogram box. And it has 100 newtons of force. A person is pushing with 100 newtons of force, which means it's going this way. Now, the coefficient of static friction on the box is 0.4. So that's our mu right there. Our mu is equal to 0.4. There's no variable for mu. It is just 0.4. It's just a value. What is the magnitude and direction of the net force on the box? Net force. Well, net force includes all the forces that are being applied on the box. So there's gravity keeping it from floating, right? If there was no gravity, it would just be flying around and floating around. So there's F of G, force of gravity. There's also a normal force being applied onto the box by the Earth, which keeps it from just tumbling into the Earth. So essentially, on flat ground, these are the same, remember, because it's cosine 0. So it's just F of G times 1 is equal to Fn in this case. So F of n is equal to F of G, which means they cancel each other out. So they actually don't really matter when we're finding the net force. But you just have to realize that those forces are there. So there's this force right here that we know about, but there's also a frictional force going on. So how do we find this frictional force? Well, frictional force is equal to normal force times this mu right here. So how do we find that? Well, we know that F of n is equal to F of G right here. So F of G is equal to mg. Well, we have m, it's 7, and we know what g is. It's negative 9.8. So that means F of G, right, 0.4 times negative 9.8. Our force of gravity is going to be equal to, our force of gravity is equal to 68.6 newtons, which means that our normal force is also 68.6 newtons. And because we're using normal force, we know that it's positive because our normal force is going up. So 68.6 times 0.4, which is our coefficient of friction, or mu, and that is our frictional force. So what is that value going to equal to? Negative 27.44. Okay? Now, whoa, these two values were positive. So why is this negative? Well, the reason why is simply because it's going towards the left, and this 100 is going to the right. And really, frictional force will always be negative because it's always opposing the actual, like, applied force. So this is like intentional, and the frictional force is a byproduct. So because it's always resisting, it's always opposing, it's negative, right? Because if you're a resisting kind of person, you always oppose things, you're a negative person. Same thing with frictional force. It's always trying to slow things down, stop things, ruin the process. Frictional force is a negative force, so it's always just negative. Same with force of gravity. Force of gravity is always down, so it's a negative force. Okay? So, negative 27.44. Well, we know that the up and down forces don't really matter, so net force is only going to consider the side-to-side forces. So all we have to do is literally net force is equal to 100 plus negative 27.44. Now, what is that equal to? Well, that's equal to 72.56 newtons, and that, my friend, is the answer to this problem. Next question. So for this question, it's not an entirely different question, but what we're trying to do now is find the acceleration, right? So I'm going to write down what we got for our net force. Our net force was 72.56 newtons. So what is the acceleration on the box? Well, that is very simple, right? So it's basically just F is equal to ma. We know that the force was equal to 72.56 of the entire box. The entire box is 7 kilograms. And so what's the acceleration of the entire box? Well, we just isolate for A. And A is equal to 10.36 meters a second squared. And that is it. There we go. Now we have our acceleration. All right, so now this is not technically a different problem, but I'm just going to explain how a lot of times you'll get to this point where, so you'll have your acceleration and now you'll have your force. And sometimes the question will want you to use this information with friction to find, say, final velocity or how far the box travels. So the way to do this is we have that it's stationary, which means v of I, initial velocity, is equal to 0. And we solve for acceleration, and it's gonna give you, say the problem was like, how far did the box travel in 5 seconds? So it'll give you another variable, right? So say it was time, 5 seconds. So then we're supposed to find change in x, or maybe it wants us to find the final velocity. Well, whatever it is, we have 1, 2, 3, and so we're essentially able to solve for these just using kinematics equations, and it's really that simple. That's it. Let's do an example doing that. Okay, so a person pushes on a 7 kilogram stationary box on the ground with 100 newtons to the left. So let's actually draw that right now. So we're on the ground. We have a box. It's 7 kilograms. And basically, it's being pushed to the left with a magnitude of 100 newtons. And then another person pushes on the same box with 30 newtons of force to the right. So this one has basically a third of the force to the right. The coefficient of static and kinetic friction between the box and the ground is 0.4. So mu is simply equal to 0.4. Calculate the net force of the people. So the net force of the people is simply just this positive 30 plus negative 100, and it's literally just negative 70 newtons, meaning that there's 70 newtons going to the left, and that's it. That is the force of the net force done by the people. So that's super easy, and the reason why we need to know that is because now that we have this negative 70 newtons to the left, that's where it's moving. We're moving negative 70 newtons. Sorry, we're moving negative 70 newtons to the left. So what that means is now using that movement, because movement means that there's friction if the problem says there's friction. If the problem says there's no friction, there's no friction. But this is the movement of the box. So now we need to find the frictional force. Well, how do we do that? Well, it's the same thing as last time, and it should be the same number, where frictional force is just normal force times mu, right? So it's just 7 times negative 9.8 again, times 0.4. So frictional force is equal to mass times gravity times mu, or the coefficient of friction, and that's all going to equal to 27.44 newtons. And the reason why this is positive is simply because our applied force is going to the left, which is negative, and that means the frictional force is going to the right, which is positive. So there we go, because it's always opposing, it's always opposite. So very simple stuff. Now we want to find the net force with friction. So this is our frictional force, and we just literally have to add this by our negative 70 to get negative 42.56 newtons. So our net force is negative 42.56 newtons, which means there are 42.56 newtons still going to the left despite the opposing frictional force. Now we have to calculate the net acceleration. So this is the movement. This is the actual movement of the box, negative 42.56 newtons. So all we got to do is literally just negative 42.56 is equal to MA, right? So 7A. So divide by 7, divide by 7, and our acceleration is going to be a negative number, which makes sense because acceleration also shows direction. So this just means that it's going to the left, and it's accelerating to the left. So this value is going to be negative 6.08 meters a second. Right? And that's our net acceleration. Now, calculate the box's displacement after 3 seconds have passed. Okay, so let's write down our acceleration. It's negative 6.08. We have time here, and we have acceleration, and we have it that is stationary, so we know what the initial velocity is. It's just 0. So we can get rid of these forces now, so we can find the box's displacement. So what do we not have? We do not have final velocity, so change in x is equal to VIT plus 1/2 AT squared, and that is just going to be equal to right, it's stationary, so 0 plus 1/2 negative 6.08 and 3 squared, which is just 9. So 9 times 1/2 is going to be 4.5, and then 4.5 times this negative 6.08 is going to be negative 27.36 meters. So that is the total displacement of the box. And that's it. I'm going to give you a mini lesson on the difference between mass and weight. So weight, like how much do you weigh, is going to be your force of gravity, which is mass times the gravitational pull towards the earth. Mass is just the mass. Do you understand? So this whole thing, mass times gravity, is weight, but mass is just mass. So what that means is you have a mass, and your mass is going to be the same on Earth, the Moon, and Mars. But if you were to be on Moon, there's a lower gravitational pull, right? Which is why you can jump so high on the Moon. And because it's lower, what does that make our weight? It's gonna make our weight also lower. Just because your mass stays the same, gravity is going down, which means your weight is also going down. So that's why you weigh less on the Moon. And yeah, your weight is less because the gravitational pull is less, but your mass is still the same. You get it? Cool. Okay, guys, so 15 kilogram box is initially at rest. A person pushes down on the box with 100 newtons of force. So we have a 15 kilogram box on the ground, and there's 100 newtons of, okay, hold on. And there's 100 newtons of force being pushed down onto the box, on top of the box. So calculate the weight of the box. So the weight of the box, right, is just F of G, which is mass times gravity. So just F of G is equal to 15 times negative 9.8, which is equal to negative 147 newtons. And that is the weight of the box. It's force of gravity. Now, calculate the normal force. So we're thinking, okay, so this is not on an incline, right? So this is F of G pulling the box down by negative 147 newtons, and we're pushing it down by negative 100 newtons. So our normal force is pushing up against both of these forces. So basically, normal force is kind of like friction. We're opposing the downward force of the box into the earth, so the earth is opposing equally that amount of force back into the box. So all it is, and this should be negative 100, so we can just add negative 147 by negative 100, which is equal to negative 247 newtons. And that is our normal force. So our normal force and our force of gravity were not the same in this question, because the weight is force of gravity, and force of gravity is a very simple equation. It's always mg. But normal force, right, depending on the scenario, it changes, but F of G is always the same. So the weight, F of G, you never have to really think about it. You can just solve. But with normal force, it does depend on the context of the situation, and that's what differentiates someone who's good at physics and someone who doesn't understand it. So it really just comes with practice and familiarity, and just really trying to understand the concept instead of just, oh yeah, I saw what you did there, it makes sense. Really try to understand what I did and why I thought that way. There's the normal force is opposing the downward force, right? It goes up. It's the earth pushing force into the object. The earth, right? It's feeling negative 247 newtons of force. That's why it's opposing that much force, if that makes sense. That's friction for you guys. See you in the next video.